the last lecture we established a basic fact that flow through pores in a perforated member is similar to flow through the pipe, because there has been a close analogy which we established between the porosity parameter and that of the Reynolds number. Considering this fact as acceptable, the velocity potential in region 1 that is the outside boundary must satisfy the following conditions. Root r this is equation number . Carefully try to understand the symbol or convention. The superscript brackets all stands for regions 1, 2 and 3. I am talking about the region 1 here, so I am using 1 here. Okay. In case of the radiation potential, I have also another count m which is standing for the number of modes 1, 2 and 3. Okay. Now the diffraction potential in all the regions will be given by there is a similarity between these three, so I am writing them simultaneously for you to easily remember. Okay. You can see here this is for region 1, so I am using argument z plus h, h is the water depth. Here I will use z plus z2, okay. Let us have the multipliers different here. This is beta n, this is gamma n. Again plus h, cos m theta, cos m theta, cos m theta. I call them as equations 15a, 15b and 15c. So, the arguments can easily understand, they are all related to the boundaries of region 1, 2 and 3. In this argument, is an Hankel's function Tmn of d, which is hm with an argument of k0r, that is an Hankel function. This is of first kind, and order m for n equals 0. All the superfix d stands for diffraction. Now, for n greater than or equal to 1, then this is given by a modified Bessel's function, which is say Km Knr, which is of the second kind and order m. Now, in this argument, in both the cases, you need to find the wave number is the positive real roots of the equation call this equation number 60. So, solve this equation, pick up only the positive real roots, and that will give you the values of Kn, which you have to use in the Hankel's function and the Bessel's function for evaluating them. Now the argument of SMN comes. We have discussed TMNs. Smn of D for n is equal to 0 and n greater than 1 is simply equal to Rm, this is R, and this is Im of beta m. We call this equation number 17. Similarly, Rmn of D for n equal to 0, for n greater than equal to 1 are given by Rm In beta n of R where Im is the modified Bessel function of first kind of order m. Further, we also need the alphas in this case, alpha, beta and gamma, these are arguments. Alpha naught is Ik naught, alpha n is Kn for n equal to 1. Beta n n pi by Z2 minus Z1. You can see this is the region we are operating the porous form, is it not? And gamma n, is it not? This is the region for region 3, n h minus b, that is the region 3. These are all for n greater than 0. I put all of them as equation number 90. Now we have seen the diffraction potential on different regions 1, 2 and 3. Now we will talk about radiation potential. in all the 3 regions. We will add similar expression phi RM1, phi RM2, phi RM3. R stands for radiation and M stands for the specific mode, and the superscript 1, 2 and 3 stands for the regions 1, 2 and 3. This is 2 omega, it is not Z, I think you agree this, okay, it is 2 omega, it is not Z, it may appear to be Z, please correct if you written as Z. Z is this, these are all limits and the boundaries, okay. In my writing it may look similar, please be careful, this is 2 omega. Summation N similarly AMN, BMN, CMN, TMN, I call them as equation number 20. Let me check these equations once again. This is A, okay. Now we can see these equations. These equations are mode dependent, you can see here. These equations are mode dependent. So these equations are mode dependent. Which satisfies the boundary conditions of solid and perforated regions. Now the function f2m r comma z is 0 for all the modes. So this has been written only to complete it in the form of the equation, whereas f3m r comma z is 0 for m equals 1, that is f31 of rz is 0, f32 and f33. This H minus B, we are talking about the second region. This is for m is equal to 2 and for m is equal to 3 now there is a multiplier here, r z plus is the whole square by h minus b minus r cube by 8 of h minus b for m is equal to 3. I call all these equations as equation 21. Let me check these equations. So in the equation earlier, that is in equation 20, you will see Tmn of r is given by the Hankel function h v k naught r of first kind and order v equal to 1, this is the order v equals 1 for m equals 1 and 3, v equals 0 for m equals 2 and for n equals 0. Okay, let us write it here. For n equals 0, it is given by the modified Bessel's function, which is k v of Kn of R, that is the argument of the Bessel function. This is of the second kind and order V equals 1 for m equals 1 and 3, V equals 0 for m equals 2 for n equal to 1. This is a small correction. This value is for n equals 0. For n greater than or equal to 1, it is given by the modified Bessel function. So, as usual we know that Kn in the argument here is the wave number which is the real positive root of the equation. Can you give me the equation number which is similar to the diffraction potential solution? What is the equation number? Kn is the root of the specific equation I said. Okay, I will write down the equation here. Gkn of tan of k and d set to 0. Let us say the arguments Smn R and Rmn is simply for n equals 0. I call this as equation number, what is the number? Where Im is the modified Bessel function. Of first kind and order m, that is it is called Im. There are some alphas and betas required in your arguments. Is Ik naught is alpha n, sorry, there is no m here, they are all simple numbers. That is the region of the boundary. That is the region of this boundary. I call this equation number 23. So, we got set of equations for understanding the diffraction potentials in the region 1, 2 and 3 and radiation potentials region 1, 2 and 3. The diffraction potentials are mode dependent and you should be able to evaluate them for different modes of m on different regions 1, 2 and 3 equation using equations 20, 21, 22 and 23 respectively. Now the coefficients of am, bn, cn of d and r are unknowns because we do not know these coefficients, okay, remaining all in the equation of set of 20 and set of 17 which is diffraction and radiation potentials on different regions are explicitly explained, except that I would like to now know the coefficients which are called unknown coefficients on this equation, which is a, b and c for diffraction and for radiation separately. Now let us say the unknown coefficients. What are these unknown coefficients? A m and d, b m and d, c m and d, these are diffraction potential coefficients, and these are radiation potential coefficients. So let us say phi of d is same as phi of region 3, these are all running for regions, d stands for diffraction potentials. How can you say 1 and 3 are same? 1 is the outer region and 3 is the region below the perforated region, okay. On a specific application r equals a, and z varies minus h and minus b, equation number 23. So now on r equals a and the variation is also true, it is an open domain again. Similarly, phi Rm1 is phi Rm3, that is the radiation potential on mth modes for region 1 and 3. On R equals A, all these expressions are valid for m equals 1, 2, 3. Now, how will you solve them is, for set of the unknown coefficients, for the set of unknown coefficients, all possible values of m are obtained, by selecting the finite series of n. Because you have to select the specific series of n and try to find out all possible values of these coefficients for different modes 1, 2 and 3. Because the velocity potential in these regions are infinite. Okay. So, in that region, for a finite series of n, for all modes, you try to estimate these unknown coefficients. That is how the solution is arrived at. So, the following algebraic equations can be generated. In matrix form can be generated after imposing the appropriate boundary conditions for different regions. Okay. You may understand and agree that A, B and C are not crossing the boundaries. If you look at the equation 17 and 20, you will see that they are applicable only for specific regions of 1, 2 and 3 respectively in diffraction and 1, 2 and 3 respectively in radiation. Okay. So, you must impose appropriate boundary condition which we already given in equation 2 and 3. What are the boundary conditions for region 1, region 2 and region 3? Impose them and read them together, apply them together with 17 and 20 sets of equations and try to get the following algebraic equation which I am writing here in a matrix form. I call this equation number 28. Where LD and RD are the matrices containing diffraction potential equations. L stands for the left hand side and R stands for the right hand side of the equation, and LR and RR are the matrices containing radiation potential algebraic equations. Similarly, L stands for the left hand side of the equation and R stands for the right hand side of the equation. XD and XR are the unknown coefficients. For different values of m and n, okay, because you have got finite series of n in this equation and possible values of modes in this problem. So, you will get different set of values on diffraction and radiation separately. So, one will be now able to find out after solving these algebraic equations, it is nothing but LD inverse of RD and LR inverse of RR. LD and LR, RD and RR will be the series of terms which you get from equation 17 and 20 after substituting their respective boundary condition, and you will get the vector XD and XR solved automatically for different m's and n's in the series. So, now you will be able to get for defined region of 1, 2 and 3 the diffraction potential and radiation potential in all the 3 regions independently 1, 2 and 3. Okay. Once you know this, you can apply this on any porous structure and find out, because now you know the velocity potential, you can easily find out the forces generated by this velocity potential in these respective region 1, 2 and 3, and accordingly sum them in the respective degrees of freedom 1, 2 and 3, which are surge, sway, surge, heave and pitch degrees of freedom, and do a conventional dynamic analysis and find out the responses. Okay. This was attempted in the previous lecture through a numerical example using star CCM plus and an experimental investigation which is done on a scaled model of 1:140. Okay. So, obviously you will not be able to validate all the 3 results on a given example problem, because these are all different types of approaches. So, obviously the results may not get validated, but an attempt was made to show you in the last lecture that how closely the experimental studies and the numerical model are getting validated with a less error of about 5 to 7% or 10% error. Okay. So, the idea of discussing this particular in this series of lectures in advanced managed structures is that we have understood that perforated cover on a given member reduces the forces on different active degrees of freedom, that is number 1. Number 2, it is one of the important and advantageous technique suggested by various researchers of reducing or controlling or limiting the secondary vibrations caused by vortex shedding frequencies. Okay, it has got 2 advantages. The greatest advantage which one can foresee is, we really want to retrofit a member in a structure in a high stress concentration zones, especially or in particular near the splash zone, because that is the area where the corrosion is maximum. So the material degradation can happen to the maximum there because of differential aeration. So one can cover the members using an outer perforated layer, and you can reduce the stresses on the members in addition to reducing the secondary vibrations caused by the vortex induced vibrations or vortex shedding frequencies on a fluid flow. Okay. So this ends the lectures on series of lectures on module 2, where we spoke or discussed flow induced vibrations, flow field disturbances caused by members kept in the flow field. Okay. So the whole idea was in the vision of discussing the force reduction or the structural response factors or parameters, the idea of discussing vortex induced vibration or flow induced structural interaction in terms of hydrodynamic perspective is not elaborately covered in these lectures. You are supposed to look into a parallel course where they talk about hydrodynamic aspects of flow induced vibrations. Okay. The perspective here was to explain in designer's point of view what would be the idea of flow induced vibration in marine structures. So this completes module 1 and 2 in total, which has explained you mostly the different kinds of problems associated with marine structures and some of the analytical, experimental and numerical difficulties of programs or problems or examples which has been discussed in 1 and 2. So we will move on to the third module later, where we will talk about the reliability studies applicable to marine structures. Thank you.